Hello, we're on to more materials questions. Continuing the streak, we've got figure 7.1 shows stress against strain graphs for three materials, X, Y, and Z, up to breaking points. Okay. State which of these three materials is brittle. Right, well, this is going to be Y is going to be brittle because it's the one that's obeying Hooke's law up to the point where it just snaps. So it doesn't have any of this ductile this sort of plastic deformation going on that we've got in X and Z, where we've got these big extensions going on for little change in the force applied. So Y is our brittle material. State one similarity between the properties of X and Y for strains less than 0.05%. So up until here, well, they both obey Hooke's law. We're both in a linear region. In fact, I mean, all right, they could have done up to 0.1%. So they are both Hookean materials for strain of that magnitude. State and explain which material has the greatest value of Young's modulus. So we need to have the steepest line, the steepest gradient in the linear region. So it has to be linear. So steepest gradient in linear region, which is clearly going to be X. But it has to be the linear bit. We can't start looking at the gradient over here in Z because this is not in the area of Hooke's law. So in which case Young's modulus is not applying. So yeah, we're going to be looking at this gradient here for X, which is greater than the one for Y. So that's dealt with those three bits. Now engineers are testing a new material to be used as support cables for a bridge. In a lab test, the breaking force for a sampled material of diameter 0.5 millimeter is 240 newtons. Estimate the breaking force for a cable of diameter 15 meters. Right, so our breaking the stress is going to be the same is what we're going to have in this. So our for the same material, at least stretched in the same way as well. So we're not getting onto fibrous stuff or anything like that. Remember with this, where it can depend on which direction you're stretching the material. We're just thinking, okay, this material is that material regardless of those nuances. So the stress will be the same for both of them. Which means our force over area is going to be the same. So for the new cable, the diameter has gone up by a factor of what's that, 30. So the area is going to go up by a factor of 900. So our force will go up, our braking force will go up by a factor of 900 as well. So we're going to have 240 multiplied by 900. So 924s would be 240 minus 24. So 216. And then we've got 1, 2, 3 zeros. 1, 2, 3 zeros. So that is 2 point, let's say 2 times 10 to the 5 newtons. All right, moving on, we got force against length graph. Okay, so make a note of that. They try to drop that in every now and again where they move away from extension to length for a spring. So they've shown that there. Explain why the graph does not pass through the origin. Right, that's because we've got length, not extension on the x-axis. State what feature of the graph shows that the spring obeys Hooke's law, so straight line, because that's the whole point of Hooke's law, that we've got that the force and the extension are proportional to each other. So that's good. The gradient of the graph is equal to the force constant K of the spring. Determine the force constant of the spring. Another one of these things, I mean, okay, they say the gradient of the graph, but it's a dead straight line. So as we've said many times before, you can just pick a pair of points off. We don't really need this, as a gradient. But I mean, we go through here, so that's going through 410. But remember, we have to take the 2 off because we need the extension, not the length. So the force constant will be 4 divided by 8 times 10 to the minus 2, which is going to be 50 newtons per meter. So that's fine. Calculate the work done on the spring when the length is increased from 2 times, from the starting point, 2 times 10 to the minus 2 to 8 times 10 to the minus 2 meters. So the work done, well, it's just the area underneath this. So we can either say that the work done is equal to a half kx squared. Well, we're going to see this is going to end up being the same. That is equal to a half fx. We've got our two options here for work done. That's just the area of this triangle. So at that point there, that looks like it's at 3 newtons. So we're going to have 3. We've got an extension of 6. So the work done is going to be a half times 3 times 6 times 10 to the minus 2, which is going to be 9 times 10 to the minus 2, 0.09 joules. So that's all of those. One end of the spring is fixed and the mass hung vertically from the other end. Mass is pulled down and then released. The mass oscillates up and down. Right, so we're going to have some simple harmonic motion going on. Figure 6.2 shows a displacement against time for the mass. Explain how you can use figure 6.2 to determine the maximum speed of the mass. You're not expected to do any calculations. So, well, we need the steepest gradient. Simple as that, really, isn't it? When we've got our displacement time graph, the speed, because we're looking here at speeds, the speed is just the magnitude of the gradient. So the steepest gradient is going to be the maximum speed. Right, we've got, what's this? Figure 7.1 shows a length of tape under tension. So it's being pulled at both ends. Explain why the tape is most likely to break at point B. Well, point B has got the highest stress. That's our force over area. And it's stress that breaks things. So yeah, it's got the same force all the way along, but the smaller area at B means it's got the highest stress. Explain what is meant by the statement, the tape has gone beyond its elastic limit. So that means, so you need to mention that we'll get deformation. So we've got a permanent extension after the stress is removed. Permanent extension after stress removed, right. So yeah, a couple of definitions there. Figure 7.2 shows one possible method for determining Young modulus of a metal in the form of a wire. So we've got the clamped wire going over a pulley with a marker, and masses hanging off the end. Describe how you can use this apparatus to determine Young's modulus of the metal. Sections below should be helpful in writing your answers. Right, well, I haven't copied the sections below across, but that isn't really going to matter. So if we're working out Young's modulus, so that's our FL over AX, which you should be familiar with now. So we've got the things that we need to measure here. So let's think again in terms of what our table would be. If we were drawing up a table of results on all of this, then we can say the things that we can control. Well, we can certainly control the force that we're going to apply. So we're going to have force that will be in newtons. So it's worth putting the units there. It helps guide what's going on. The original length, that's just fixed for the whole thing, isn't it? So we can measure that at the beginning in meters. The original cross-sectional area, I mean, this is for the same wire, so we're not changing either of these, so we can measure these at the start. Then we've got our experimental variable here, the thing that's going to be changing, which is the extension, which we're also going to measure in meters. And then we're going to need some kind of, well, calculate. We've got a couple of options, so I'll get onto this in a bit. You could either calculate it, say, okay, well, now we can just put all of these numbers in. We've got all of them, and we can calculate Young's modulus. Or you might want to say, well, let's do the, say, force divided by the extension. We could do a force extension graph, something like that. It depends how you want to, I suppose, if you were going to plot something in the conventional way, we'd have the thing that we fixed on the x-axis and the thing that we're measuring on the y-axis. We'd have this straight line then going through the origin, which means that the gradient would be L over A times the Young's modulus. So we've got two different ways of going about this, but we've got this set up already. So this is certainly going to help now for getting our marks, because we can say what we're going to do with each one of these. So we can say, let's measure L and A. So we'll start off, say, measure the length in meters using meter rule. So, this is all of our usual formulaic approach. What are we going to measure using what? We can measure the diameter using a micrometer, and then work out the A, then calculate area, the cross-sectional area. Then we can say we can vary the number of masses on there. So yeah, we'll just say we can hang masses on wire, and say that the force is equal to the mass times the acceleration due to gravity. Measure extension using meter rule. So you can see how formulaic all of this is, how we do all of our experiment questions, really. And then we get on to the last bit of, well, what are we going to do then? You can either say calculate Young's modulus equals FL over AX, and then do multiple measurements and average, because that's essentially the same as plotting the graph. So we could say that, or instead of that bit, we could say plot X against F and gradient equals L over AE. So we've got two options at the end. You don't have to, they seem to be really obsessed with drawing graphs and taking the gradient when it comes to Young's modulus, but you really don't have to. So either one of those approaches would be fine, providing you're still doing some kind of multiple measurement thing here if you're just doing the calculation. But we're going through the same process. I can't emphasize this enough. I mean, I might be overstating it the number of times I go through all of these sort of things, but every single experiment question that you get, you can approach in exactly the same way. There shouldn't be really any way of not getting full marks on these, because you're doing the same thing every single time. And okay, you can leave the bullet points actually out when you're writing it up, but these are just individual sentences. Measure this using that. Calculate this using this formula, plot this graph and measure that gradient. It's the same approach every time. We've got quite a lot of text going on in this one. Right, so in what form is energy stored when a metal wire is extended by a force? Right, okay, apart from the fact we're not a massive fan of forms of energy, energy is energy, but their elastic potential energy is what we're getting at on that. A metal wire of length 1.2 meters is clamped vertically. Weight is hung from the lower end of the wire. The extension of the wire is 0.35 millimeters. Cross-sectional area of the wire is that. The Young's modulus is that. Calculate the strain. So the strain, what have we got in all of this? They've given us L and X and A and Young's modulus. So they've given it, so strain is extension over length, which is 0.35 times 10 to the minus 3 divided by 1.2. So typing that in, we've got, okay, it's not a straightforward number, it's going to be slightly less than a 3. So we've got 2.9 times 10 to the minus 4 times 10 to the minus 4, and that doesn't have any units for strain. And the tension in the wire, Young's modulus is, so that's stress over strain, which is equal to force over area times strain. So the force is going to be the Young's modulus times the strain times the area. So we just worked out the strain, multiply that by 1.9 times 10 to the 11, and then multiply it by cross-sectional area, 1.4 times that. So we've got 7.8. And how many did we have? We had a -4, a -7, and a +11. All right, so that all cancels out by the look of it. So we've got F equals 7.8, 7.76, so 7.8 newtons, which at least sounds pretty reasonable. Right, part C. There's great excitement at the moment about structures known as carbon nanotubes. Excellent. They're cylindrical tubes of carbon atoms. These cylindrical tubes have diameter of a few nanometers and can be several millimeters in length. Right, so they are very long, or at least in one dimension compared to the other. Several millimeters isn't long, but compared to nanometers wide, it certainly is. Carbon nanotubes are one of the strongest and stiffest materials known. Recently, a carbon nanotube was tested to have an ultimate tensile strength of 60 gigapascals. Wow. In comparison, high carbon steel has an ultimate tensile strength of about 1.2 gigapascals. Under excessive tensile stress, the carbon nanotubes undergo plastic deformation. This deformation begins at a strain of about 5%. Carbon nanotubes have a low density for a solid, have recently been used in high quality racing bicycles. Right, the diameter of carbon nanotubes is a few nanometers. What is a nanometer in meters? Right, that's 10 to the minus 9 meters. Explain what is meant by plastic deformation. We've had this a lot. So this is that you've got a permanent extension of the material once the stress has been removed, or once the force has been removed. How many times stronger are carbon nanotubes than high carbon steel? So they're both in gigapascals, so we've got 60 divided by 1.2, which is going to be 50. State 2 advantages. So I thought we were going to get a bit more in the way of calculation of all this, especially as they've given us percentage and things, but it doesn't look as though we've got any more calculations to do. State 2 advantages of making a bicycle frame using carbon nanotube technology rather than high carbon steel. Well, we know for a start that they're stronger. That's 50 times stronger, and they've also told us that they're low density, so they're much lighter. So yeah, this last part seems to be an exercise of reading a paragraph of material and pulling some information out of it rather than doing anything else.